There are stars that dazzle us with sheer brilliance, stars that collapse into violent black holes, and stars that grow into cosmic behemoths dwarfing our Sun. Yet among all of these, there exists one quiet, faint, and unassuming star that has shaken the very foundations of our understanding of the cosmos. It does not shine the brightest, nor does it sit at the center of a grand nebula, but its existence alone is a contradiction so bold that some astronomers call it the impossible star. This star is known as Caffau's star, a faint speck hidden in the halo of our Milky Way. At first glance, it may look ordinary, but the closer scientists looked, the more it defied everything we thought we knew about how the universe works. According to the prevailing model of cosmology, the Big Bang Theory, stars like Caffau's star should not exist in our universe today. And yet, there it is, ancient, stubborn, and almost mocking our understanding of cosmic history. Why does this little star matter? Because the universe is supposed to follow rules. According to those rules, the earliest stars, often called population 3 stars, were massive, short-lived, and metal-free. They should have burned bright and died quickly, leaving no direct survivors. Later generations of stars, the ones we see today, including our own Sun, were born with heavier elements, forged in the hearts of earlier stars, and scattered across space through supernovae. This recycling process means that every star born after the earliest era should contain at least some of those heavier elements: iron, carbon, oxygen, and so on. But here lies the problem. Caffau's star contains almost none. It is almost pristine, a fossil seemingly plucked straight from the infancy of the universe. The presence of such a star raises a chilling question. Could our understanding of the Big Bang and the way stars formed afterward be incomplete, or even fundamentally flawed? Astronomers are trained to expect anomalies, but some anomalies are so deep that they shake the pillars of science itself. Caffau's star is one of those. What makes this so fascinating is that this is not a blazing beacon visible to the naked eye. It's a star so faint, so unremarkable in brightness, that only powerful telescopes and careful analysis revealed its peculiar nature. And yet, from this dim glow, an enormous contradiction emerges. If our theories of cosmic evolution are correct, this star shouldn't have survived, or perhaps shouldn't have even formed at all. Think of the universe as a great puzzle, with billions of pieces that astronomers are slowly putting together. Over centuries, we've constructed a grand picture of reality. The Big Bang set the stage, galaxies formed, stars were born and died, and their deaths seeded the cosmos with the elements necessary for planets, life, and everything we see around us. But Caffau's star is like a piece of that puzzle that doesn't fit anywhere. You try to force it into place, but no matter how you rotate it, the edges don't align. It's as though the universe is whispering, there is something you have missed. And that is what makes Caffau's star so captivating. It's not merely another dot in the night sky. It's a cosmic riddle, an ancient messenger, and perhaps a silent challenger to one of the most successful scientific theories ever proposed. The Big Bang Theory has explained so much, from the cosmic microwave background radiation to the expansion of galaxies. Yet here is this single star, stubbornly resisting explanation. For astronomers, this isn't just an odd curiosity. It's a reminder that the universe has a way of surprising us, even humbling us. The cosmos doesn't bend itself to our theories. Our theories must adapt to the cosmos. And sometimes it only takes one contradiction, one faint star, to reopen questions that seemed long settled. Caffau's star, the impossible star, reminds us that cosmic history is far from complete, and that perhaps the early chapters of the universe hold secrets still beyond our reach. The story of how this strange star was uncovered begins not with a single moment of revelation, but with years of patient searching. Astronomers have long hunted for ancient stars, sometimes called stellar fossils, hidden within the Milky Way. These stars act as windows into the distant past, because the oldest ones carry in their atmospheres the chemical signatures of the universe as it was billions of years ago. Most of the time, these searchers turn up low metallicity stars, rare but not unheard of. But in 2011, a team led by Elisabetta Caffau, working with the European Southern Observatory's Very Large Telescope in Chile, came across something extraordinary. They were combing through the Sloan Digital Sky Survey, which had catalogued millions of stars, looking for candidates that might show unusually low metallicity. Among the data, one faint star stood out. At first glance, it looked like another low-mass, ancient star, one of the many sprinkled across the galactic halo. But once the light of this star was analysed in detail with the high-resolution spectrograph at the Very Large Telescope, the results were nothing short of shocking. Instead of showing the expected traces of metals, small amounts of iron, carbon, oxygen, or magnesium, the star's spectrum was almost barren. It had less iron than any star ever observed, to the point where its metallicity was over 20,000 times lower than that of the Sun. To astronomers, this was staggering. It was as if the star had formed in a universe that had not yet been enriched by previous generations of stellar explosions. What truly surprised the team was not just the star's poverty of metals, but the fact that it was still shining, quietly burning hydrogen billions of years after its birth. By all conventional understanding, such a star should not exist today. The earliest stars in the universe, the so-called population 3 stars, were theorized to be massive and unstable, burning out quickly and leaving no survivors. Later generations, the stars we know and see around us, were supposed to inherit at least some heavy elements forged in those violent deaths. Yet here was a star with almost none, existing as though it had been born before the first stars had ever exploded. When the team published their results, it caused ripples across the astrophysics community. How could a star this primitive be hiding in our galaxy? Was it truly a relic from a time before the universe was seeded with heavier elements, or did its existence point to an overlooked mechanism of star formation? For many astronomers, the discovery of Caffau's star was more than just a curiosity. It was a challenge, a reminder that our neat models of cosmic evolution might still have missing pieces. This was not the first time a star had raised eyebrows, but few discoveries had struck at the core of cosmology in such a direct way. Every measurement reinforced the same conclusion. The star's metallicity was so vanishingly small that it pushed the boundaries of what was thought possible. It wasn't just old, it was ancient beyond expectation, its very nature whispering of a universe still young, still raw, and still shrouded in mystery. For astronomers at the time, the feeling was akin to unearthing a living dinosaur. By all logic, it should not have survived to the present day, and yet, against all odds, there it was, a quiet, faint beacon from an epoch we believed was forever lost to history. What makes this faint little star so extraordinary is not its brightness, its mass, or even its position in the galaxy, but its very makeup, the ingredients that formed it. When scientists examined its light and carefully broke it down through spectroscopy, they discovered something astonishing. Caffau's star has almost no metals at all. In astronomy, metals doesn't mean just iron or gold or silver. It refers to every element heavier than hydrogen and helium. And this star is so stripped of those elements that it is considered one of the most primitive stars ever found in the Milky Way. Our Sun, for comparison, contains about 2% metals by mass, tiny, but enough to shape planets, drive stellar evolution, and provide the building blocks for life. Even other old, metal-poor stars, found in the halo of the galaxy, typically contain some trace of heavy elements, a kind of fingerprint from the explosions of earlier stars. But Caffau's star is different. Its iron content is so low that, to put it into perspective, if you were to scoop up the same amount of material from the Sun and compare it, the Sun would have more than 20,000 times as much iron as this faint star. That number alone puts it in a category of its own. What makes it even stranger is that this isn't simply a matter of lacking iron. Caffau's star also shows an unusual deficiency in carbon. Most extremely metal-poor stars, the few that have been discovered, tend to show at least some carbon enhancement, thought to help in the cooling process of star-forming gas clouds in the early universe. Carbon acts as a coolant that allows primordial clouds to collapse and form low-mass stars. Without it, theory predicts that clouds of hydrogen and helium wouldn't fragment easily, meaning stars like Caffau's star shouldn't be able to form in the first place. Yet here it is, existing in defiance of that rule. This makes Caffau's star a cosmic paradox. It's too metal-poor to belong comfortably to the population of stars we expect to survive to the present day. It lacks the carbon signature we would anticipate if it formed in unusual conditions. And yet, it quietly endures as a low-mass star, still fusing hydrogen billions of years after its birth. In a sense, this star is like a time capsule from the universe's earliest days, containing almost nothing beyond the raw hydrogen and helium created in the Big Bang itself. It hasn't been heavily polluted by supernovae or enriched by stellar recycling. It's as if this star slipped through the cracks of cosmic history, remaining untouched and unaltered while the rest of the universe moved on. That's why many scientists call it a fossil star, a remnant of a time so ancient it seems almost impossible that it could still be shining today. Its very existence forces us to ask unsettling questions. Did our models of star formation in the early universe miss an alternative pathway that allowed stars like this to form and survive? Or is this star a once-in-a-universe rarity, a cosmic fluke that somehow managed to be born in conditions we thought impossible? Either way, what makes it special is not just that it is poor in metals, it's that its entire being seems to stand as evidence that our neat story of cosmic evolution is not yet complete. When astronomers talk about metals in stars, they aren't thinking in the same way we usually do here on Earth. To most of us, metals mean shiny, solid materials like iron, copper, gold, or silver. But in astrophysics, the definition is much broader and much simpler. Everything heavier than hydrogen and helium is considered a metal. That means oxygen, carbon, nitrogen, silicon, iron, calcium. All of them count as metals in the cosmic sense. The reason for this unusual definition is rooted in the Big Bang itself. In the first moments after the universe was born, about 13.8 billion years ago, only the simplest elements were created. The overwhelming majority of the universe was hydrogen, with helium making up most of the rest, and just a trace amount of lithium. Nothing heavier existed. The periodic table as we know it, the oxygen we breathe, the carbon in our DNA, the iron in our blood, all of those heavier elements came later, forged inside stars. This means that the very first generation of stars, the so-called population 3 stars, were made entirely of hydrogen and helium, with no metals at all. They burned fast, lived short lives, and died spectacular deaths. Only through those deaths, through supernova explosions and other extreme processes, did metals spread into the cosmos. So when astronomers look at a star and measure its metallicity, what they are really measuring is how many generations of stars came before it. A star with high metallicity, like our Sun, is evidence of countless cycles of birth and death. Previous stars that exploded and seeded the galaxy with metals that eventually made their way into new stars. A star with low metallicity, by contrast, is closer to the beginning of the chain. Its gas cloud wasn't heavily enriched by earlier stars, which makes it a direct window into a more primitive stage of the universe. This is why metallicity matters so much. It doesn't just tell us about the star itself. It tells us about the history of the universe at the time the star was born. By examining metallicity, scientists can trace the timeline of cosmic enrichment, essentially using stars as fossils to reconstruct the family tree of the cosmos. A high metallicity star is like a product of modern civilization, carrying the fingerprints of countless predecessors. A low metallicity star is more like an ancient relic, untouched and closer to the original raw materials of creation. Now, here's where things get even more fascinating. Metallicity isn't just a historical marker. It also plays a critical role in star formation and survival. In star-forming clouds, metals act as coolants. They help gas clouds shed energy, allowing them to collapse into smaller fragments that can form stars. Without metals, gas clouds don't cool as easily, which means they tend to collapse into larger, hotter, more massive stars. That's why astronomers believed the first stars in the universe were giants, many tens or even hundreds of times more massive than the Sun. These giants would have burned through their fuel in just a few million years, brief sparks on the cosmic timescale, before collapsing into black holes or exploding as supernovae. So in theory, a star like Caffau's star shouldn't have been able to form. With virtually no metals and no significant carbon or oxygen to help cool the gas cloud that birthed it, it should have been impossible for such a low-mass star to condense. And yet, there it is, a small, faint star that has survived for billions of years, quietly burning hydrogen as though nothing were unusual about its existence. To appreciate how strange this is, think about the way astronomers categorize stars. Population 1 stars, like the Sun, are rich in metals and are considered relatively young. Population 2 stars, found mostly in the halo of the galaxy, are older and poorer in metals, but still contain some heavy elements. Population 3 stars are hypothetical, the very first stars, metal-free and long gone. Caffau's star doesn't fit neatly into any of these categories. It is too metal-poor even for a typical population 2 star, yet it is not massive or short-lived like a population 3 star should have been. It's like an intruder in the timeline, belonging to a chapter of the universe we thought had already closed. This is where metallicity becomes a kind of cosmic detective tool. Every time we measure it, we expect to confirm the big picture, that as time passes, stars are born with more and more metals. This gradual increase matches the predictions of the Big Bang and stellar evolution models. But when a star like Caffau's star shows up with virtually no metals, billions of years after the first stars should have seeded the universe, it's as though the detective finds a fingerprint that doesn't match anyone in the database. It hints at a missing piece, an unknown process, or perhaps a flaw in our assumptions. The presence or absence of metals also has consequences for life itself. Without metals, you can't form rocky planets. You can't form the complex chemistry needed for biology. Our very existence is tied to the process of stellar enrichment. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was once forged inside a star and spread across the galaxy by violent stellar deaths. So when we find a star that has almost no metals, we are essentially looking at a world where the building blocks of life were absent. It's a glimpse into a universe before life, before planets, before chemistry as we know it. And this is why astronomers were so stunned by Caffau's star. Its metallicity is not just low, it is vanishingly small, to the point where it forces us to ask whether our assumptions about the early universe are too simplistic. Perhaps star formation in the early cosmos was more complex than we believed. Perhaps stars could form under conditions we didn't think possible, using physics that we still don't fully understand. Or perhaps, more provocatively, our grand model of cosmic evolution, the Big Bang itself, has cracks that are only now being revealed. When you hear scientists talk about metallicity in stars, it might sound like a dry technical term. But hidden within that word is a story as big as the universe itself. Metallicity tells us about time, about death and rebirth, about the recycling of cosmic matter across billions of years. And in the case of Caffau's star, metallicity tells us about something else too, the persistence of mystery, the stubbornness of the cosmos, and the possibility that our most trusted theories might not yet capture the whole truth. According to the story we have built around the Big Bang, stars like Caffau's star should be utterly impossible. The Big Bang itself set the initial conditions. A universe filled with hydrogen, helium, and a trace of lithium, but nothing else. No carbon, no oxygen, no iron, none of the heavier elements that now make up planets, oceans, atmospheres, and even our own bodies. From this soup of simplicity, the very first stars, the mysterious population 3 stars, were supposed to arise. But here's the catch. Without metals to help the cooling process, the gas clouds that birthed those first stars could only collapse into very large objects. This means those first stars had to be massive, often tens or even hundreds of times more massive than our Sun. And because massive stars burn fast and die young, none of them should still be shining today. They should all have collapsed into black holes or exploded as supernovae billions of years ago, long before the Milky Way ever formed. By that logic, every star still visible in the universe today should contain at least some of the heavy elements created by those early generations. The explosions of population 3 stars were supposed to seed the universe with metals, gradually enriching the gas clouds that formed later generations. That's why our Sun has a decent share of metals, because countless stars before it lived, died, and scattered their remains into space. Even ancient stars in the halo of our galaxy, which are among the oldest known, almost always show at least a faint trace of those metals. The very existence of those elements in their atmospheres is proof of the cosmic cycle of death and rebirth. But then comes Caffau's star, a star so metal-poor that it almost looks like a population 3 relic, yet it clearly isn't one of those short-lived giants. Instead, it's a low-mass star that has somehow endured across the entirety of cosmic history, nearly as old as the universe itself, yet with a composition so primitive it belongs to an earlier age. If our models are right, it simply shouldn't be there. The rules of stellar formation tell us that without enough carbon, oxygen, or other cooling agents, gas clouds cannot fragment into small, long-lived stars. And yet, this is exactly what Caffau's star seems to have done. It formed in defiance of those rules, a small, faint, hydrogen-burning star that has managed to survive for billions of years. In other words, it exists in a space between theory and reality, a loophole in the laws we thought were unbreakable. To appreciate just how shocking this is, it helps to picture the universe as a kind of timeline. The first stars ignite at one end, massive and brief. They explode, filling the cosmos with metals. After them, new generations form, each progressively richer in heavy elements. By the time you get to galaxies like the Milky Way, most of the stars should show the fingerprints of this enrichment. A star with almost no metals left in the modern era is like stumbling across an untouched fossil in a museum where everything else has already been catalogued and cleaned. It shouldn't just be rare, it should be impossible, because the conditions to create it supposedly vanished billions of years ago. This is why some astronomers, when they first studied Caffau's star, described it as a kind of cosmic trespasser. It doesn't belong in our current universe. It belongs in a chapter of history that was supposed to be long finished when the first stars were still being born. If you were to build the universe out of equations, probabilities, and models, you would never expect to find such a star in your simulation. And yet, our telescopes have found it, quietly burning, ignoring the rules we thought were inviolable. The problem goes deeper still. If stars like this exist, it means that our understanding of star formation in the early universe might be flawed. It could mean that some low-mass, ultra-metal-poor stars did form in the earliest epochs, even though theory says they shouldn't have. And because low-mass stars live for billions upon billions of years, they could still be here, scattered across the galaxy, hiding in plain sight. If that's true, then Caffau's star may not be a lone anomaly. It could be the first of many fossils, each one a silent contradiction to our cosmic models. And that is the heart of the mystery. According to Big Bang cosmology, according to stellar physics, according to every model we've built, Caffau's star should not exist in today's universe. But it does. Its faint glow is a reminder that reality doesn't always match our expectations. And sometimes the universe writes a story far stranger than the ones we imagine. The idea of the universe's first stars is one of the most fascinating chapters in cosmic history. Astronomers call them population 3 stars, and they were unlike anything we see today. These were the very first stars to ignite after the Big Bang, born in a cosmos still young, raw, and almost entirely unpolluted by the heavier elements that fill our universe now. At that time, the universe was composed almost exclusively of hydrogen and helium, the lightest elements created during the Big Bang's first few minutes. There was no carbon, no oxygen, no iron, none of the heavier elements that we associate with planets, life, and even the stars we see today. That meant the first stars had to form in an environment stripped to its most basic ingredients, relying only on hydrogen and helium gas clouds collapsing under their own gravity. Because they lacked heavier elements, what astronomers call metals, these stars behaved very differently from modern ones. Metals help stars cool and regulate the process of collapse, and without them, population 3 stars could only form by gathering immense amounts of hydrogen and helium. The result is that many of these first stars are believed to have been monsters, far larger and more massive than the stars we're used to. Some may have been hundreds of times the mass of our Sun, burning hotter, faster, and brighter than almost any star alive today. Their energy output would have been staggering, flooding the universe with light at a time when it had only just emerged from cosmic darkness. But their brilliance came at a cost. Stars this massive live fast and die young. While a star like our Sun can shine for 10 billion years, a population 3 giant would have consumed its fuel in just a few million years, a blink of an eye on the cosmic scale. When they died, they didn't fade quietly. Many of them would have ended their lives in colossal supernova explosions, or even more violent hypernovae, scattering the first heavier elements into space. Those explosions seeded the universe with carbon, oxygen, iron, and all the building blocks that would later form planets, life, and even us. In that sense, these long-gone stars were the ancestors of everything we know. Without them, the universe would still be a barren ocean of hydrogen and helium, with no chemistry complex enough to give rise to galaxies, solar systems, or biology. Because of their extreme size and brief lifetimes, astronomers don't expect any population 3 stars to still exist today. Billions of years have passed since their formation, and any star massive enough to qualify as a true first-generation star would have burned itself out long ago. Smaller stars, like red dwarfs, can live for trillions of years, so theoretically, some low-mass population 3 stars might still be out there. But the catch is that forming small stars without metals is incredibly difficult, since metals are key to the cooling processes that allow smaller clouds of gas to collapse. That's why most scientists believe the first stars were overwhelmingly massive, short-lived, and are now gone forever. What we do see instead are their descendants. The heavy elements forged in their fiery deaths were incorporated into the next generation of stars, the so-called population 2 stars, which are metal-poor compared to modern ones, but still enriched compared to the very first. These stars are ancient, many of them billions of years old, and they help us study what conditions must have been like in the early universe. Our own Sun belongs to an even later generation, population 1, which contains the most metals, having formed in a universe already recycled through countless stellar births and deaths. This is why the search for population 3 stars has become one of the holy grails of modern astronomy. Detecting one would be like finding a living fossil, a direct window into the dawn of starlight itself. Scientists use telescopes like the James Webb Space Telescope to look deeper into time, trying to glimpse the light from galaxies so ancient that they might still contain some of these elusive stars. So far, none has been found with absolute certainty. The closest we've come are stars like Caffau's star, objects so deficient in metals that they seem almost primordial, but still not completely devoid of heavy elements. Even the most metal-poor stars discovered to date contain at least a trace of carbon or oxygen, suggesting they are not truly first generation, but rather members of the second. The expectation that population 3 stars are gone is based on both theory and observation. Theory tells us they should have lived short lives due to their immense masses, while observation has yet to reveal a star with absolutely zero metals. But the absence of evidence hasn't closed the case. It's possible that some rare, low-mass population 3 stars could still be quietly burning, hidden in the far reaches of the galaxy, too faint for our current instruments to detect. If we were ever to find one, it would be one of the most groundbreaking discoveries in the history of astronomy, rewriting our understanding of star formation and the early universe. Their expected absence also carries a profound implication. Everything we see around us, from the planets beneath our feet to the atoms in our bodies, is the product of their deaths. We are, quite literally, the ashes of population 3 stars. Their lives may have been short, but their legacy is eternal, woven into the very fabric of the cosmos we inhabit today. Caffau's star, despite being so incredibly metal-poor, is not truly a population 3 star. By definition, population 3 stars would have absolutely no metals at all. They would be made purely of hydrogen and helium, the untouched ingredients of the Big Bang. Since astronomers have yet to find a single true population 3 star still burning, Caffau's star does not quite qualify. Instead, it is placed into the category of population 2 stars, the ancient, metal-poor stars that formed after the very first stars seeded the universe with heavier elements. Population 2 stars are old, but not primordial. They contain tiny traces of metals, enough to show they formed from material that had already been slightly enriched by previous generations of stars. Caffau's star fits here, but it is an anomaly because its metallicity is lower than almost anything astronomers have ever seen in the Milky Way. To put this into perspective, most population 2 stars have metallicities that, while small, are still measurable. They may have iron content that is 1/10, 1/100th, or even 1,000th that of the Sun. Caffau's star, on the other hand, has iron content measured at less than 1/200,000th of the Sun's. That number is so small, it almost reads like 0. This makes it unique even among its peers, because while population 2 stars are expected to be poor in metals, they are not supposed to be this poor. The level of deficiency suggests a nearly primordial origin, one that overlaps uncomfortably with the realm of population 3 stars. Astronomers were stunned to find that a star could exist in such an in-between state, straddling categories and resisting simple classification. The oddity becomes clearer when considering star formation theory. According to conventional understanding, metals play a critical role in cooling the gas clouds that collapse to form stars. Without metals, gas remains hot, turbulent, and difficult to condense. This is one reason population 3 stars are thought to have been so massive. Only huge clumps of hydrogen and helium could collapse in the early universe, without the help of metals to cool and fragment them. In later generations, once metals were present, smaller stars could form more easily because the cooling process was efficient. Caffau's star seems to break this rule. With virtually no metals, it should not have been able to condense into such a small, long-lived, low-mass star. It contradicts the expectation that extreme metal-poor environments only produce giants that quickly burn out. This is why scientists sometimes refer to it as a relic star, or even a fossil star. It appears to be a direct bridge between the population 3 era and the population 2 era, almost as if it slipped through the cracks of cosmological history. Yet, labeling it neatly proves challenging. If it were a population 3 star, it should have no metals whatsoever. If it were a normal population 2 star, it should have at least some trace of metals beyond what we see. Instead, Caffau's star seems to live in a grey area, a liminal space where categories blur. It forces astronomers to rethink how strict the boundaries between stellar populations really are. The discovery also raises questions about how widespread stars like it might be. If one such relic exists in our galactic neighborhood, might there be others scattered across the halo of the Milky Way? Are they remnants of a forgotten epoch, overlooked because they are so faint and difficult to detect? Or is Caffau's star truly one of a kind, a statistical outlier born of extremely unusual conditions? Each of these questions touches the heart of why its classification is so puzzling. It does not behave like a typical population 2 star, but nor does it fully qualify as population 3. It is instead a reminder that nature is not bound to the neat labels humans create. The universe often produces exceptions that defy expectations, and Caffau's star is perhaps the most striking exception of all in the study of stellar populations. Caffau's star drifts quietly in a region of the Milky Way that most of us never think about, the galactic halo. Unlike the luminous disk, where the spiral arms unfurl and new stars continue to ignite in bright nurseries of gas and dust, the halo is a ghostly, sparsely populated sphere surrounding the galaxy. It is filled not with the shining bands of youthful stars, but with some of the oldest, faintest, and most mysterious objects in existence. This is where Caffau's star resides, far from the bustling galactic neighborhoods that dominate astronomical images, instead occupying the quiet outskirts like an ancient wanderer, untouched by the chaos of younger generations. Its location alone is a clue to its strange nature, because the halo is thought to preserve relics of the galaxy's earliest history. Stars that formed billions of years ago often linger there, orbiting the Milky Way in elongated, eccentric paths, as though they are fossils circling the galactic heart. Finding a star in the halo is not unusual. Astronomers have catalogued many halo stars, most of which are population 2, meaning they have low but detectable amounts of metals compared to the Sun. What makes Caffau's star astonishing is not just that it was found in the halo, but that its metallicity is practically non-existent. The halo is a kind of time capsule, but even within that time capsule, stars like this should not exist. According to cosmology, the halo preserves stars from the early waves of galactic building blocks, small proto-galaxies that later merged into the Milky Way. But even those ancient progenitors should have already undergone enough stellar recycling to enrich their stars with traces of heavier elements. Yet here, tucked away in this quiet region, astronomers stumbled upon a star so pristine that it looks almost like it leapt directly out of the first age of the universe. Its location also matters because halo stars provide critical evidence for reconstructing galactic archaeology. By mapping their chemical signatures, velocities, and orbits, astronomers can essentially reverse engineer the history of the Milky Way, discovering how smaller galaxies merged to form the one we inhabit today. Many halo stars are thought to have originated outside the Milky Way entirely, brought in when dwarf galaxies were swallowed by our own. This raises an intriguing question about Caffau's star. Did it form here in our galaxy, or was it once part of a tiny, primitive dwarf galaxy that merged with the Milky Way billions of years ago? If the latter is true, then Caffau's star is not just an odd relic, but potentially a messenger from a long-destroyed system, carrying within its faint glow the chemical memory of an ancient cosmic environment now erased. The halo's remoteness also helps explain why such a star survived at all. The galactic disk is full of dynamic processes, supernova explosions, star formation bursts, molecular clouds collapsing and dispersing, all of which can disrupt, pollute, or erase ancient populations. But the halo is quiet, isolated, and largely free from the raw materials needed for new star birth. That means stars that formed billions of years ago can drift there unperturbed, orbiting slowly for eons, too dim to attract attention until a telescope like the Very Large Telescope carefully sifts the faint light from the surrounding darkness. In a sense, the halo is the universe's attic, a place where forgotten relics remain preserved simply because nothing has disturbed them. Caffau's star is one of those relics, tucked away in the shadows, waiting to be discovered. And yet, its presence in the halo complicates our understanding of galactic evolution. If stars with such extraordinarily low metallicity are still out there, hidden in the outskirts, how many others might exist? For decades, astronomers assumed that stars this primitive simply could not survive. Population 3 stars, the very first generation, were expected to be massive and short-lived, leaving no survivors. Population 2 stars, like those in the halo, were supposed to contain at least small traces of metals, enough to indicate that their birth clouds had already been seeded by earlier stellar explosions. But Caffau's star sits awkwardly between these categories. Its home in the halo supports the idea that it is ancient, but its chemical profile is so stripped down that it challenges the very assumptions used to categorize stellar populations in the first place. Even its orbit matters. Halo stars often follow elongated paths around the galaxy, unlike the nearly circular orbits of stars in the disk. This suggests that many halo stars were captured from other galaxies, their unusual orbits reflecting a violent history of galactic mergers. Caffau's star likely shares this trait, though its exact origin is still debated. Its orbit may hint at whether it was born in a small, primitive system or within the early halo of the Milky Way itself. If astronomers can trace its motion precisely, they might learn whether this star is an immigrant from an ancient dwarf galaxy or a true native relic of our galaxy's first days. In either case, its halo location underscores that the Milky Way is not just a single entity, but a patchwork, stitched together from countless smaller systems across cosmic time. Perhaps the most profound implication of Caffau's star's halo residence is what it tells us about the possibility of other, similar stars hiding beyond the reach of our current instruments. The halo is vast and sparsely surveyed compared to the disk. If one such star was found almost by chance, then there may be many more, still waiting to be uncovered. Each one would be a living fossil, an untouched record of conditions nearly 13 billion years ago. For cosmologists, this is like discovering a dinosaur bone in your backyard. It proves that relics from epochs thought long gone may still linger, hidden in plain sight. And with next-generation telescopes probing ever deeper, the halo may reveal more of these time travelers, rewriting our understanding of how the first stars formed and how galaxies like ours evolved. The fact that Caffau's star resides in the Milky Way's halo is not just a matter of location. It is central to the mystery. Its environment preserved it long enough for us to find it. Its orbit hints at a history of galactic cannibalism and mergers. Its pristine chemistry sets it apart even among other halo stars. And its very existence reminds us that the outskirts of galaxies are not empty wastelands, but rather cosmic archives, holding the secrets of the earliest ages of the universe. The halo is where the galaxy hides its oldest stories, and in the faint light of Caffau's star, we catch a rare glimpse of a chapter that challenges everything we thought we knew about the universe's past. When astronomers study Caffau's star, one of the most mind-bending realizations they confront is its incredible antiquity. This star is not just old in the casual sense, it is ancient on a cosmic timescale, nearly as old as the universe itself. To put this into perspective, the universe is about 13.8 billion years old, formed in the wake of the Big Bang. The very first stars, known as Population 3 stars, were born just a few hundred million years after that event, marking the beginning of starlight in an otherwise dark cosmos. Most stars we see today are much younger, formed after billions of years of cosmic evolution, when galaxies had already matured and heavy elements were circulating through the interstellar medium. But Caffau's star stands as a relic of an era when the universe was still very young, and its chemical fingerprint reveals that it could have formed more than 13 billion years ago, making it almost as old as time itself. The reason scientists estimate such an extraordinary age is linked to its composition and position in the Milky Way. With virtually no metals, elements heavier than helium, it indicates that it was born in a time before many stellar generations had lived and died to enrich the galactic environment. Metals are produced in the cores of stars and spread into space by supernovae, gradually building up the chemical diversity we observe in later stars, planets, and life itself. When a star lacks these metals, astronomers interpret that as a sign it formed in a nearly pristine universe, before the cosmic recycling process had much of a chance to take hold. Caffau's star is so metal-poor that it must have formed after only one or perhaps a handful of previous stellar explosions, making its birth date staggeringly close to the dawn of galaxies. Dating stars isn't like reading a calendar. It relies on models of stellar evolution and the chemistry of the universe itself. But all signs point toward Caffau's star being among the first generation of so-called Population 2 stars. Population 3 stars, the very first, are believed to have been massive, short-lived, and now extinct, gone within a few million years of their births. Caffau's star, however, is different, small, quiet, and long-lived. Stars of its mass, significantly lower than that of the Sun, can persist for billions upon billions of years because they burn their fuel extremely slowly. This makes them cosmic survivors, able to shine faintly for nearly the entire age of the universe. It's the combination of its extreme, metal-poor nature, its small size, and its continued presence that tells scientists this star was born not long after the Big Bang and simply endured, unnoticed, until our telescopes grew powerful enough to find it. Its survival is astonishing when you consider the violent history of the Milky Way. Over billions of years, galaxies collided, merged, and reshaped one another. Our own galaxy grew from these cosmic encounters, sweeping up stars, gas, and dark matter into the majestic spiral we see today. Many of the oldest stars ended up in the galactic halo, a vast, diffuse sphere surrounding the Milky Way's disk. Caffau's star belongs to this halo population, which is a natural place to search for survivors from the universe's youth. That placement itself reinforces the idea of its ancient age. Halo stars tend to be among the oldest in the galaxy, gravitationally bound but distant from the bustling star-forming regions in the disk. Its estimated age, 13 billion years or more, means it has been shining since nearly the very beginning. Imagine what it has witnessed in cosmic terms: the birth of the first galaxies, the epoch of rionization when the universe transitioned from opaque to transparent, the growth of clusters and cosmic structures, and the eventual formation of the Sun, Earth, and every living thing that would one day gaze at the night sky. While life on Earth has only been around for a sliver of cosmic history, Caffau's star has been there from almost the start, quietly glowing through eons of change. This raises fascinating philosophical questions. When we look at Caffau's star, we aren't just seeing a distant point of light. We are looking at a messenger from the dawn of time, a physical survivor from an age when galaxies were young, when the building blocks of future worlds had barely begun to form. It is almost incomprehensible to think that this same star has been out there, unchanged, for over 13 billion years, while everything else, the stars around it, the galaxies near and far, even our own place in the cosmos, has been in constant transformation. Its very existence challenges our sense of permanence and change, reminding us that some things can endure across cosmic history, bridging the gap between the universe's violent beginnings and the present age of telescopes and technology. And yet, its ancient age is also a scientific puzzle. According to standard cosmology, stars like Caffau's shouldn't have formed so easily in the early universe. Without metals, the cooling of primordial gas clouds should have been inefficient, making it nearly impossible for such a low-mass star to condense. Instead, theory predicts that the first stars were massive and short-lived. That makes Caffau's star a contradiction, a star that not only survived for nearly the full age of the universe, but also managed to form under conditions where its very existence was thought improbable. It's as if it slipped through a loophole in the laws of astrophysics, sneaking into creation when it shouldn't have had the means to do so. The fact that it is still burning today is a gift to astronomers. It offers a living fossil, a chance to directly observe material from the early cosmos. Unlike most ancient stars that have since died and scattered their remains into space, this one is still intact, still holding on to its secrets in its faint light. Studying its age and composition allows researchers to test theories of star formation, galaxy evolution, and even cosmology itself. The very fact that it is nearly as old as the universe blurs the line between observation and time travel. By studying this star, scientists are peering directly into the conditions that existed at the dawn of the Milky Way. In many ways, Caffau's star reminds us that the universe is far more mysterious and unpredictable than we sometimes assume. For all our models and equations, reality still manages to surprise us, offering relics of ages long past, scattered like hidden clues across the cosmos. And as this star quietly continues its faint glow, nearly 14 billion years after the Big Bang, it stands as a humbling reminder of both our fleeting existence and our deep connection to the ancient past of the universe. Caffau's star is not just old and metal-poor, it is chemically baffling in ways that continue to frustrate astronomers and cosmologists. The central mystery lies in its chemical composition, or more accurately, in what it lacks. Unlike almost every other star studied in our galaxy, this star is nearly devoid of the heavy elements we normally expect to find, even in the most ancient stars. To appreciate how unusual this is, we need to step into the world of stellar chemistry, where astronomers probe light from stars to read their chemical signatures, like a cosmic fingerprint revealing their life history. When we talk about metals in astronomy, we are referring to everything heavier than helium. That includes carbon, oxygen, iron, silicon, and many other elements forged inside stars and spread across space through supernova explosions. The first stars, population 3, were formed from pristine hydrogen and helium created in the Big Bang, and they contained virtually no metals at all. Later stars, population 2, like Caffau's, inherited some fraction of these metals from their predecessors. This gradual enrichment is why most stars, even the ancient ones, show at least traces of carbon and iron. Yet in Caffau's star, the levels are astonishingly low, so low that its existence alone is a cosmic riddle. To put its metallicity in perspective, the Sun's iron content, which astronomers use as a benchmark, is defined as solar metallicity. Most stars in the halo of the Milky Way, which are ancient and metal-poor, might contain about 1/1000th or 1/10,000th of the Sun's iron content. Caffau's star, however, contains less than 1/20,000th of the Sun's iron, so little that it is virtually undetectable. In fact, when researchers first analyzed its light spectrum using the Very Large Telescope in Chile, they were stunned to find iron levels so low that they had difficulty measuring them at all. This means that the gas cloud from which it formed was almost untouched by earlier generations of supernovae, which is not supposed to happen this late in cosmic history. Carbon, too, is nearly absent, and this is where the puzzle deepens. Normally, astronomers expect metal-poor stars to contain at least some carbon, because even the earliest supernovae, explosions of population 3 stars, should have seeded the surrounding space with carbon-rich material. That carbon plays a critical role in the cooling of gas clouds. Without carbon, nitrogen, or oxygen, a cloud of hydrogen gas has difficulty cooling down enough to collapse into a star. In other words, by all our models, the cloud that gave birth to Caffau's star should not have been able to fragment and condense into a low-mass star at all. Yet it did. This means either the cooling process was somehow assisted by an unknown mechanism, or our understanding of star formation in the early universe is incomplete. Other elements are similarly scarce. Magnesium and calcium, two products of massive stars, are also present at extremely low levels. The expected fingerprint of prior stellar generations, The ashes of earlier stars that usually pepper later-born stars are conspicuously absent. This is what makes Caffau's star so extraordinary. It seems to have sidestepped the enrichment process altogether. The mystery doesn't end there. When researchers compared its composition to models of nucleosynthesis, they found mismatches. For instance, stars that formed shortly after the first supernovae should display a distinct pattern of element abundances, some elements appearing in relative abundance compared to others. But Caffau's star doesn't follow those patterns. Its chemical fingerprint looks more primitive, more pristine, as if it belongs to an era much closer to the dawn of the cosmos. And yet, paradoxically, it still exists today, billions of years later, shining faintly in our galactic halo. This bizarre composition raises difficult questions. Did Caffau's star somehow form from a pocket of nearly untouched primordial gas, isolated from the cycles of stellar death and rebirth that enriched the galaxy? Or was it born under completely different conditions, perhaps in an environment where the first supernovae expelled most of their metals away, leaving behind clouds of nearly pure hydrogen and helium? Some researchers even suggest that the star's unusual composition hints at new physics or new pathways of stellar formation not accounted for in current theories. What makes the situation even stranger is the fact that stars like Caffau's are expected to be rare, possibly one in tens of millions. And yet, the discovery of even one such object means that our galaxy harbors relics of an almost primordial past, hidden among the more normal halo stars. It raises the unsettling possibility that our current theories of chemical evolution are missing something fundamental, and that the story of how the Milky Way's oldest stars formed is more complex than we imagined. In essence, the chemical composition of Caffau's star is like a time capsule from an earlier universe, one that contradicts the rules of stellar chemistry as we know them. It has almost no iron, almost no carbon, and almost none of the other heavy elements that should have been unavoidable by the time it formed. This scarcity is not just unusual, it is nearly impossible to explain with standard astrophysical models. And that is why Caffau's star is not only one of the most primitive stars ever discovered, but also one of the most confounding. The Big Bang Theory lays out a very specific sequence of events for how the elements in our universe came to be, and those predictions extend directly to the stars we observe. When we look at a star like Caffau's star, we are confronted with a problem. Its chemical makeup doesn't seem to match what those models predict. To understand why this is such an issue, we need to revisit what the Big Bang Theory says about the origin of the elements, and then compare that roadmap to what astronomers actually see when they measure the composition of this strange star. According to the Big Bang Theory, the first few minutes of the universe were an inferno of nuclear activity. This period, known as Big Bang nucleosynthesis, was when the first atomic nuclei formed. But the reactions that could occur under those early, hot, and rapidly expanding conditions were limited. The vast majority of the universe's matter became hydrogen, with helium making up most of the remainder. A tiny sprinkle of lithium and beryllium was also produced, but nothing heavier. That's because the temperatures and densities dropped too quickly for nuclear reactions to build up elements like carbon, oxygen, or iron. So, in that first era, the entire universe was basically a sea of hydrogen and helium, with almost no metals, the astronomical term for all elements heavier than helium. This elemental starting point means that when the first stars ignited, those mysterious population 3 stars, they were born out of nearly pure hydrogen and helium gas. Without metals to help cool the collapsing clouds of gas, those first stars were thought to be extremely massive, hot, and short-lived. They would have burned brightly, lived only a few million years, and then exploded as supernovae, seeding the surrounding gas with heavier elements. Those explosions were crucial. They began the chain reaction of chemical enrichment that allowed later generations of stars, planets, and eventually life itself to exist. Now here's the key prediction. Once those first stars seeded the universe with metals, no later star should have formed without at least a trace of those elements. Even if the enrichment was uneven, the idea is that by the time a galaxy like the Milky Way had developed its halo, disk, and bulge, all the gas available for star formation would have been contaminated by at least some fraction of heavy elements from earlier supernovae. Later stars, population 2 and population 1, were expected to all carry the fingerprints of this chemical history. That's why the discovery of Caffau's star is so unsettling. It is a population 2 star, meaning it formed after the first stars had already lived and died. Yet its chemical makeup looks almost indistinguishable from what one would expect of a primordial population 3 star. It has vanishingly little iron, very little carbon, and almost no detectable heavier elements at all. This is what cosmological models say shouldn't happen. If it formed later, as its classification suggests, the raw material from which it condensed should have contained at least a little more metal pollution. But when astronomers look at this star's spectrum, it's practically metal-free. The problem isn't just the lack of metals, but the specific absence of certain elements that models predict should be common even in the oldest stars. For example, supernovae of the first generation should have released carbon, oxygen, and nitrogen into the interstellar medium. Stars forming afterward, population 2 stars, should therefore almost always have measurable amounts of those elements, especially carbon. Carbon is particularly important because it acts as a coolant in star-forming clouds. Without carbon, gas has trouble radiating away heat and therefore has difficulty collapsing into small, low-mass stars. This is why the discovery of a low-mass, carbon-poor star like Caffau's star is such a direct contradiction of theory. The expectation was that any star with such low metallicity should not exist at all, because the physics of gas cooling and fragmentation requires some carbon and oxygen to help form small stars rather than giant, short-lived ones. If Caffau's star truly lacks those cooling agents, it should never have condensed into a long-lived, low-mass star in the first place. It should either have failed to form, or it should have been massive and short-lived, disappearing billions of years ago. Yet here it is, quietly orbiting in the halo of the Milky Way. What makes this even stranger is that the Big Bang theory itself is not in question here. Its predictions about the initial production of hydrogen and helium are very well tested, confirmed by the cosmic microwave background and observations of primordial gas clouds. The difficulty lies in the astrophysical models layered on top of the Big Bang, the assumptions about how the first stars formed, how they exploded, and how efficiently they seeded the next generation with metals. The very existence of Caffau's star forces astrophysicists to reconsider those steps. Perhaps the first stars didn't enrich their surroundings as uniformly as expected. Perhaps some regions of gas clouds stayed pristine longer than models assumed. Or perhaps our understanding of how stars cool and condense in metal-free environments is incomplete. This star is a stark reminder that the universe is not always neat and predictable. The Big Bang theory set the stage, but the unfolding of stellar and galactic evolution may have had more twists and irregularities than scientists originally thought. If a star with virtually no metals can still exist today, that means there are gaps in our models of star formation, chemical evolution, and perhaps even the early dynamics of the Milky Way itself. Instead of being a quiet confirmation of theory, Caffau's star has become a disruptive clue, one that says our current picture is missing something essential. And this isn't just an isolated anomaly. Over time, astronomers have uncovered other extremely metal-poor stars, though few are as extreme as Caffau's star. Each one adds weight to the idea that our models of early star formation are incomplete. The broader implication is that the transition from population 3 to population 2 stars wasn't as clean or uniform as the textbooks suggest. Instead, it may have been messy, irregular, and patchy, leaving behind rare survivors like Caffau's star that defy neat categorization. What's remarkable is how much one star can challenge an entire framework. The Big Bang theory predicted the first elements. Cosmology predicted the rise of stars and galaxies. Astrophysics predicted that every later generation of stars should bear the chemical fingerprints of their predecessors. And yet, here is a star that seems to have slipped through all those predictions, surviving as a relic from a forgotten chapter of the universe's history. It doesn't disprove the Big Bang, but it does show that the pathway from the universe's birth to its present state may be far more complex and surprising than we imagined. Astronomers, when confronted with the puzzle of Caffau's star, were forced to admit that its existence is not just an oddity, but potentially a crack in the carefully constructed framework of cosmic evolution. In standard cosmology, after the first few 100 million years following the Big Bang, the first stars, those pure hydrogen and helium population 3 giants, lived short, violent lives. Their supernovae seeded the universe with carbon, oxygen, iron, and countless other heavier elements, giving rise to the next generations of stars. These new stars, the so-called population 2, were expected to show clear traces of enrichment. And yet, here we find a star, still burning in the Milky Way halo, that seems to have skipped this enrichment entirely. It is almost devoid of the metals we would expect. The big question then is, how did it form, and how has it survived? One explanation that has been put forward is that Caffau's star formed in an environment that somehow missed the cosmic enrichment process. Imagine a pocket of gas in the early universe, cut off from the turbulent mixing caused by supernova explosions. In this isolated region, the hydrogen and helium gas could have remained pristine for billions of years longer than cosmologists once thought possible. Eventually, conditions may have allowed a star to coalesce from this untouched reservoir. If true, then Caffau's star is a rare fossil from a forgotten fragment of the early cosmos, preserved against the odds in the outskirts of our galaxy. But skeptics point out that cosmic mixing is incredibly efficient on large scales. When stars explode, their debris spreads far and wide, carried by powerful shock waves and galactic winds. For a gas cloud to remain pristine long enough to form a star like this, it would require extraordinary isolation, something difficult to reconcile with our current models of galactic evolution. Another hypothesis revolves around the cooling mechanisms required for star formation. For a gas cloud to collapse under its own gravity, it must shed heat. In the earliest universe, hydrogen and helium alone were not very good at cooling. Astronomers long believed that heavier elements, even in tiny amounts, were necessary to allow clouds to cool sufficiently for star formation. But Caffau's star challenges that. If it formed with almost no metals, then perhaps there are overlooked pathways for cooling that involve molecular hydrogen or even exotic physics such as fine-tuned quantum effects. This idea suggests that our understanding of star birth is incomplete, and that stars may be able to form in conditions we never thought possible. A related explanation suggests that Caffau's star is not entirely pristine, but rather formed from gas that had been lightly seeded by the very first supernovae. Those early explosions may not have spread their elements evenly, but instead enriched the universe in a patchy, uneven way. In some places, heavier elements like iron were abundant. In others, the enrichment leaned toward lighter elements such as carbon and oxygen. Perhaps the gas that birthed Caffau's star was enriched in such an unusual, unbalanced manner that iron, in particular, was nearly absent, leaving the star with its baffling composition. This could mean that what we're observing is not a metal-free star, but a star with an exotic chemical fingerprint, a relic of one of the universe's earliest, strangest supernovae. There's also the idea that Caffau's star may have once had more metals, but somehow lost them. Some theories suggest that strong stellar winds or other mechanisms could strip a star's outer layers, leaving behind an apparent deficiency in metals. Yet this explanation is unsatisfying for many astronomers because the star is relatively small and stable. Its winds are not powerful enough to have blown away such a massive portion of its material. nor is there evidence of violent interactions with nearby stars or objects that could have stripped it clean. As a result, the loss scenario, while intriguing, remains unlikely. Another speculative theory is that Caffau's star may represent a failed population 3 star, a kind of leftover from the very first generation. Perhaps, instead of being entirely massive and short-lived, some population 3 stars were smaller than expected and managed to survive across cosmic time. If Caffau's star is one of these survivors, it would be a genuine relic of the universe's dawn, a living piece of the Big Bang itself. But this idea creates tension with computer simulations, which consistently show that metal-free stars should not form in low-mass varieties. Without metals to aid in cooling, gas clouds should collapse into massive stars only, burning hot and fast, not into the relatively modest star we see in Caffau's case. For such a low-mass population 3 star to exist, something fundamental in our cooling models must be incomplete or wrong. Some astronomers even wonder whether dark matter could have played a role. In the early universe, dark matter clumps may have acted as gravitational seeds, pulling gas into small, stable pockets. If dark matter interactions contributed to cooling in some subtle way, perhaps they allowed stars like Caffau's star to form in conditions that would otherwise be impossible. This line of thought is highly speculative and difficult to test, but it opens a doorway to an even deeper mystery. Perhaps stars like this don't just challenge our understanding of stellar physics, but also our grasp of the very ingredients of the cosmos. No single explanation is fully satisfying. Each has strengths, but each also runs into major problems when compared with observations and theoretical models. The isolated gas pocket theory explains the lack of metals, but struggles with the reality of cosmic mixing. The exotic cooling pathway idea accounts for star formation in near-pristine gas, but lacks strong evidence in simulations. The patchy enrichment theory makes sense on paper, but doesn't fully explain the extremely low iron content. The lost metals idea requires processes we don't observe in such stars. And the survivor hypothesis, Caffau's star as a long-lived population 3 star, directly contradicts the dominant understanding of how star formation worked in the early universe. What all of these theories point toward, however, is that Caffau's star is forcing astrophysicists to confront the limits of their models. It is like a cosmic riddle that refuses to be solved, a silent witness to a universe much stranger than we had assumed. Perhaps the real explanation is something none of these theories has touched upon. A new kind of physics, a subtle twist in the early universe's story, or even a process of star formation we have not yet conceived. Until more stars like Caffau's are found, it remains a lone enigma. But if more are discovered, then the entire history of the cosmos may need to be rewritten. Caffau's star is not only an enigma because of its chemical makeup and extreme age, but also because it highlights one of the most perplexing puzzles in stellar astrophysics, the black hole formation problem. In the early universe, the first generations of stars were thought to be incredibly massive. Simulations consistently show that the pristine hydrogen and helium gas from the Big Bang could only form stars many tens to hundreds of times the mass of our Sun. These were the population 3 stars, the cosmic behemoths that blazed briefly before dying in catastrophic supernovae or collapsing directly into black holes. The physics behind this is well understood. Massive stars exhaust their nuclear fuel extremely rapidly, and without sufficient pressure from lighter elements to slow down their collapse, they naturally implode under gravity's unrelenting pull, forming black holes in the process. If that picture is correct, then the universe should have been littered with the remnants of these titanic early stars. Black holes, both stellar and intermediate in mass, should dominate the remnants of the first epoch of star formation, leaving very few survivors that are low mass and long-lived. By contrast, Caffau's star is relatively small, much smaller than the Sun, and has survived for over 13 billion years. Its existence raises a fundamental question. How did it avoid the fate predicted for stars formed in the early universe? According to classical theory, stars forming in a gas cloud with such low metallicity and under the intense pressures of early galactic environments should either be massive enough to collapse into black holes or fail to form at all due to insufficient cooling. Yet Caffau's star clearly defied this expectation. The black hole formation problem becomes even more complicated when considering the mechanisms that drive stellar evolution in the metal-free early universe. Metals, which are absent in the first gas clouds, play a critical role in radiative cooling and in moderating the pressure and temperature inside a forming star. Without metals, gas clouds contract more slowly, but also tend to fragment into fewer clumps. This leads to the formation of very massive stars, and massive stars, in turn, are fated to burn their fuel quickly and die violently, often ending their lives as black holes. Caffau's star, however, is not massive. It is a low-mass star that should never have formed under these primordial conditions. Its small size, combined with its almost complete lack of metals, presents a direct contradiction. The physics that governed early star formation predicted no survivors like it. Adding to the paradox, the early universe was an intensely dynamic environment. Gas clouds were subjected to shock waves from nearby supernovae, intense ultraviolet radiation from other massive stars, and gravitational interactions within forming galaxies. In such turbulent conditions, even forming stars that avoided immediate collapse into black holes faced significant threats. They could be torn apart, disrupted, or prevented from stabilizing long enough to ignite sustained nuclear fusion. Yet somehow, Caffau's star not only formed, but stabilized, igniting fusion and surviving for billions of years in relative isolation. The odds against this happening are staggering when compared with our theoretical models, making its existence one of the most confounding mysteries in modern astrophysics. Some theories attempt to explain this apparent defiance of early universe physics. One idea suggests that Caffau's star may have formed in a region where the conditions were atypical, such as an unusually low-density environment that allowed a smaller star to condense without triggering massive collapse. Another proposes that turbulence and fragmentation in the gas cloud may have been more efficient than models predict, allowing the formation of low-mass stars even in nearly metal-free conditions. Yet these explanations remain speculative. Current simulations of early star formation struggle to replicate such conditions consistently, and even when they attempt it, the resulting stars rarely match the precise mass, composition, and longevity of Caffau's star. There is also the possibility that unknown physics is at play. Some astrophysicists suggest that we may be missing a key piece of the puzzle in our understanding of stellar collapse and the interaction between gravity, gas pressure, and radiation in primordial clouds. Perhaps low-mass stars could survive under conditions previously thought impossible, or maybe early stars possessed mechanisms to shed mass efficiently, avoiding collapse into black holes. Alternatively, some have even speculated that exotic forms of matter, or interactions involving dark matter, could have influenced the formation and survival of early stars. While speculative, these hypotheses highlight just how fundamentally Caffau's star challenges our current cosmological framework. Another angle to consider is the timeline of supernova feedback in the early universe. Massive population 3 stars went supernova quickly, distributing metals and radiation that would prevent the formation of pristine stars nearby. For Caffau's star to form after these events, it must have either emerged in a remarkably isolated pocket of gas or have formed before the supernovae could contaminate its region. Either scenario is improbable, which reinforces the black hole formation puzzle. In theory, most early stars should have been either destroyed, collapsed into black holes, or transformed the surrounding environment to prevent low-mass star formation. Yet Caffau's star appears to have sidestepped all these cosmic hazards. The black hole formation puzzle is more than a curiosity. it has deep implications for our understanding of cosmic evolution. If stars like Caffau's can survive for billions of years under conditions thought impossible, then the early universe may have been far more diverse than previously imagined. Perhaps low-mass stars could form more easily than current simulations suggest, or maybe the thresholds for stellar collapse are not as rigid as we assume. Either way, the existence of a star that should, by all accounts, have either collapsed into a black hole or failed to form entirely, forces scientists to reconsider the very rules that govern star formation in the universe's infancy. Even more intriguingly, this puzzle ties into larger questions about the distribution of black holes and the remnants of the first stars. If Caffau's star is one of the few survivors of a class of stars that should have been rare or non-existent, it raises questions about what else might have survived, or what we have yet to discover. Are there other low-mass, metal-poor stars hiding in the halo or in neighboring galaxies that have quietly persisted for nearly the full age of the universe? Could these stars reveal a hidden population that challenges our assumptions about how many black holes formed in the early universe? These questions make Caffau's star a linchpin in our effort to reconstruct the universe's formative years. The survival of Caffau's star is a humbling reminder of nature's ability to defy expectation. We construct models, run simulations, and derive equations to predict the cosmos, yet a single star can quietly exist, shining for billions of years, and expose gaps in our understanding. In many ways, this star serves as a cosmic anomaly that refuses to be ignored, compelling scientists to confront the uncomfortable possibility that the universe is more complex, more nuanced, and more unpredictable than we ever imagined. Its continued presence challenges the inevitability of black hole formation in the early universe and opens a window into alternative paths of stellar evolution that may have been overlooked or underestimated. Caffau's star thus stands as both a relic and a puzzle, a silent witness to the earliest epochs of cosmic history. It forces a reconsideration of assumptions about mass, metallicity, and survival in the harsh conditions of the young universe. And while much work remains to reconcile theory with observation, the black hole formation puzzle underscores a simple truth. The universe still holds secrets that even the most sophisticated models have yet to account for. Its existence demands both humility and curiosity, reminding us that in the grand theatre of the cosmos, sometimes the smallest players, faint, ancient stars, can challenge the biggest ideas. Caffau's star has not only challenged conventional models of stellar evolution and cosmology, it has also prompted some of the most speculative and thought-provoking alternative theories about the universe itself. While mainstream astrophysics focuses on established processes, Big Bang nucleosynthesis, supernova enrichment, star formation thresholds, and galactic chemical evolution, the stubborn anomalies presented by stars like Caffau's have encouraged scientists, and occasionally more fringe theorists, to imagine scenarios that stretch beyond conventional thinking. These alternative theories are controversial, yet they are crucial because they force us to question whether our foundational assumptions about the cosmos are complete, or if we might be missing an entirely new layer of physics or cosmic history. One of the first alternative ideas involves rethinking the very timing and uniformity of chemical enrichment in the early universe. Most models assume that after the first stars exploded as supernovae, metals dispersed relatively uniformly across the primordial gas, gradually increasing the metallicity of subsequent generations. Yet Caffau's star seems to have formed from material almost entirely untouched by these processes. Some theorists suggest that enrichment might not have been a smooth, continuous process at all. Instead, it could have been chaotic, highly localized, and sporadic, creating pockets of near-pristine gas even well after the first generation of stars had lived and died. If true, it implies that our models of the early universe's chemical homogeneity are oversimplified, and that the universe may have contained multiple coexisting zones with vastly different chemical compositions. In this scenario, Caffau's star is a survivor from one of these rare pockets, but it also raises questions about what other anomalies might be lurking undetected in the galaxy. Some fringe theories go even further, suggesting that our understanding of the Big Bang itself may be incomplete. While the Big Bang theory is robustly supported by a wealth of observational evidence, including the cosmic microwave background and the expansion of the universe, it primarily describes the formation of hydrogen, helium, and trace lithium. It does not directly predict the formation and distribution of stars in the complex galactic environment billions of years later. Alternative cosmologies propose that early universe conditions may have allowed for localized variations in fundamental constants or physics that we have yet to observe. For example, some models speculate that in certain regions, the rate of nuclear reactions in the earliest stars could have differed, producing unusual elemental distributions that allowed rare low-mass stars to form. While highly speculative, these ideas underscore the possibility that stars like Caffau's might be evidence of physical processes beyond our current understanding. Another provocative hypothesis involves dark matter. Most astrophysical models assume dark matter interacts only gravitationally. But what if it also played a more direct role in the formation of early stars? Some theorists propose that clumps of dark matter in the early universe could have acted as stabilizing scaffolds, allowing gas clouds to collapse into low-mass stars despite the lack of metals. These dark matter interactions might have altered the density and pressure balance within the cloud, effectively enabling star formation under conditions previously thought impossible. While there is no direct evidence for this mechanism yet, Caffau's star provides a tantalizing hint that such processes may have occurred. If true, it would imply that our understanding of the interplay between visible matter and dark matter in the early universe is incomplete, and that the first stars may have formed under a more diverse set of conditions than conventional models predict. Time itself has also been proposed as a variable factor. Some fringe cosmological models suggest that certain regions of the universe might experience subtle variations in the progression of time or the rate of expansion on very small scales. In this context, pockets of gas that appear to us as existing billions of years later might have undergone star formation under conditions resembling an earlier cosmic epoch. Such theories are controversial and difficult to test, but they highlight the kinds of radical thinking that Caffau's star encourages. If localized time anomalies or variations in expansion rate existed, they could explain why a star with almost primordial composition could form long after the universe's first stars had already enriched the interstellar medium. There is also a line of thought that entertains the possibility of previously unknown pathways of star formation. In conventional astrophysics, the presence of metals is crucial for cooling and condensation, yet Caffau's star suggests there may be alternative mechanisms. Some theorists speculate that quantum processes, molecular hydrogen interactions, or even exotic particles may have provided the necessary cooling for low-mass stars to form in metal-poor environments. While these ideas remain largely untested, they suggest that the fundamental physics of star formation may be more versatile than previously assumed. If so, Caffau's star is not just an outlier. It is a window into a set of cosmic rules that we have barely begun to explore. Fringe cosmologists also consider the possibility that the early universe might have experienced previously unrecognized events, such as mini-reheating phases, delayed recombination in certain regions, or microscale fluctuations in density and temperature that allowed low-mass star formation. These events could have left behind pockets of gas that defy standard enrichment timelines. In such a scenario, Caffau's star would not be a violation of the Big Bang or stellar evolution per se, but rather evidence of subtle environmental effects in the early universe that our models have so far overlooked. Some alternative theories even venture into the realm of multiverse speculation, suggesting that Caffau's star could have originated in a region of the cosmos governed by slightly different physical constants, only to be transported into our observable universe through mechanisms like gravitational interactions or cosmic flows. While this idea borders on the highly speculative and untestable, it highlights the lengths to which some scientists are willing to go to reconcile the star's existence with our understanding of cosmic history. In essence, Caffau's star acts as a boundary marker for the limits of our current theories, forcing the scientific community to consider phenomena that may not fit neatly within conventional paradigms. The star raises philosophical as well as scientific questions. Could it be that our frameworks are too simplified to account for the stochastic nature of the early universe? Perhaps the first few billion years were not a uniform, predictable progression, but a chaotic patchwork process, full of rare events that leave behind exceptional survivors like Caffau's star. If so, its existence is both a challenge and an invitation. A challenge because it exposes gaps in our knowledge, and an invitation to expand our theories, to explore new physics, and to consider cosmic scenarios that lie beyond the boundaries of traditional astrophysics. Caffau's star, in its silence and simplicity, compels us to think radically. Every alternative theory, whether invoking isolated gas pockets, dark matter scaffolding, quantum cooling processes, or even subtle variations in the fundamental laws of physics, shares a common thread: the realization that our universe may be far more flexible and unpredictable than our current models allow. While mainstream science focuses on probabilities and averages, this star reminds us that nature is not obligated to conform to expectation. Outliers like Caffau's are not just curiosities, they are signposts pointing toward the unknown, guiding astronomers and cosmologists to revisit foundational assumptions, challenge conventional wisdom, and imagine the universe in ways that were previously unthinkable. The alternative theories surrounding Caffau's star are not mere flights of fancy. They are serious intellectual exercises, motivated by the uncomfortable fact that our best models cannot fully explain what we observe. Whether these theories ultimately prove correct, or whether more conventional explanations eventually emerge, the star serves as a catalyst for deeper inquiry. It is a reminder that the cosmos is not a static, predictable machine, but a dynamic, intricate system full of mysteries, some of which may require entirely new physics to understand. Caffau's star may be a single point of light in the Milky Way halo, but it illuminates profound questions about the very origins of matter, the formation of stars, and the unfolding history of the universe itself. Caffau's star becomes even more extraordinary when compared to other ancient stars, particularly the famous Methusela, also known as HD 102915+172927. Methusela has long been celebrated in astrophysics for its remarkable age, estimated at around 14.46 billion years, brushing up against the age of the universe itself. Its discovery shocked astronomers because it seemed to have formed so soon after the Big Bang, challenging conventional timelines for early star formation. Methusela's very existence pushed the boundaries of stellar evolution theory, forcing scientists to confront the possibility that low-mass stars could form almost immediately after the universe's birth. Yet, while Methusela is already a remarkable relic, Caffau's star presents a puzzle that is even harder to reconcile with standard models. The Methusela star is extraordinarily metal-poor, containing only traces of elements heavier than helium, yet it still fits within the expected parameters for a low-mass population 2 star. Its chemical composition shows slight enrichment from previous generations of massive population 3 stars. This enrichment allowed the gas cloud from which Methusela formed to cool sufficiently and condense into a star without defying known physical principles. In other words, Methusela is a near-primordial star, but it still conforms, more or less, to the expectations of early cosmic chemical evolution. Its metals, though scarce, are sufficient to explain its formation and survival over billions of years, according to established astrophysical theory. Caffau's star, on the other hand, pushes these boundaries to an unprecedented degree. Its metallicity is far lower than Methusela's, showing an almost complete absence of iron, carbon, and other heavy elements. This makes it one of the most chemically primitive stars ever detected, a true fossil of the early universe. Where Methusela represents the earliest stars we expected to exist, Caffau's star represents a type of star we did not anticipate could survive the intense conditions of the post-Big Bang universe. Its existence implies that either star formation can occur under conditions previously thought impossible, or that our understanding of early cosmic enrichment is missing critical details. The age comparison also emphasizes Caffau's star's unique significance. Methusela is astonishingly old, nearly matching the universe in age, yet its formation and survival are theoretically plausible. Caffau's star, by contrast, combines extreme age with a near-total lack of metals and a relatively low mass, a combination that is extraordinarily difficult to explain. Most low-mass stars forming from near-pristine gas would require special cooling mechanisms, yet our standard models suggest that without metals, gas clouds should collapse into massive stars that would burn out quickly or collapse into black holes. Caffau's star survived where theory predicts it should not, making it an anomaly of both chemical and structural evolution. Additionally, Caffau's star's location in the halo of the Milky Way highlights its rarity in contrast to Methusela. While Methusela is relatively close to the Sun and has been extensively studied, Caffau's star resides in a region where surviving pristine or nearly pristine stars are exceptionally rare. Its existence in such an environment suggests either an extraordinary degree of isolation from supernova enrichment or a formation mechanism that allowed it to persist unaltered over billions of years. This makes Caffau's star a much more extreme test case for theories of star formation and chemical evolution in the early universe. Comparing the two also underscores the theoretical challenges they pose. Methusela fits into existing models with minor adjustments. Caffau's star, by contrast, forces more radical reconsideration of early stellar physics. Its existence suggests that either our understanding of the cooling processes in metal-poor gas clouds is incomplete, or that there were unique pockets in the early universe where normal enrichment did not occur. It may even hint at processes or interactions that standard models have not yet accounted for, from variations in early supernova feedback to interactions with dark matter or other exotic cosmic phenomena. In essence, while Methusela is extraordinary because it is nearly as old as the universe, Caffau's star is extraordinary for combining age, extreme metal deficiency, and survival in a way that is fundamentally at odds with conventional astrophysics. Methusela teaches us about the earliest star formation within known theoretical constraints. Caffau's star challenges the very assumptions that underpin those constraints. It is a living reminder that the universe can produce anomalies that force scientists to question even their most well-established theories. Caffau's star's significance grows when considering the broader population of ancient stars. Many metal-poor stars exist, but few approach the combination of low mass, extreme metal deficiency, and survival over 13 billion years that Caffau's star exhibits. Methusela is a benchmark for extreme age, but Caffau's star is a benchmark for extreme rarity, demonstrating conditions and outcomes previously thought impossible. Its very existence compels astronomers to refine their models of early star formation, explore alternative cooling mechanisms, and consider whether other rare survivors might still be lurking, hidden in the halo or other distant reaches of our galaxy. In short, while Methusela is a monumental find in understanding the universe's early history, Caffau's star eclipses it in the degree to which it defies expectation. Where Methusela confirms that low-mass, metal-poor stars could form soon after the Big Bang, Caffau's star suggests that stars could form under conditions that were, by all conventional accounts, effectively forbidden. Its rarity, chemical purity, and enduring survival make it a cosmic anomaly of unparalleled significance. a star that does not merely tell us about the past, but challenges our fundamental understanding of how the universe evolved. Detecting a star like Caffau's star is a task that stretches the limits of modern astronomy, and it underscores the sheer difficulty of studying the universe's most ancient relics. Unlike bright, metal-rich stars that dominate the night sky, Caffau's star is extremely dim, faintly twinkling in the halo of the Milky Way, far away from the galactic disk where most stars congregate. Its low luminosity alone makes it difficult to observe. The star emits far less light than its more metal-rich counterparts because of its small mass and low energy output, meaning astronomers must rely on highly sensitive telescopes and sophisticated imaging techniques to even locate it. Observing faint stars requires long exposure times, precise instrumentation, and an ability to separate the star's weak light from the background noise of cosmic radiation, interstellar dust, and the diffuse glow of other stars. The star's distance also complicates detection. Located in the galactic halo, tens of thousands of light-years away from the Sun, Cathau's star is essentially on the outskirts of our observational reach. The halo itself is a sparsely populated region filled with faint stars, globular clusters, and dark matter, all of which contribute to a challenging observational environment. Unlike stars in the galactic disk, which are relatively close and abundant, halo stars require meticulous surveys and careful selection criteria to identify candidates for further study. Large-scale surveys, such as the Sloan Digital Sky Survey, provide the wide-field imaging needed to pick out potential ancient stars, but even then, identifying a true metal-poor candidate among millions of stars is like finding a needle in a cosmic haystack. One of the key observational challenges is measuring metallicity in stars like Caffau's. Astronomers rely on spectroscopy to determine the chemical composition of a star, splitting its light into a spectrum and analyzing the absorption lines created by different elements. In metal-poor stars, these lines are exceptionally weak, almost at the edge of detectability. For Caffau's star, the iron lines, carbon lines, and other metal indicators are barely discernible, demanding telescopes with high spectral resolution and extremely low noise levels. Even slight interference from atmospheric turbulence, interstellar gas, or instrumental limitations can compromise the accuracy of these measurements. Achieving the precision necessary to confirm the star's near absence of metals is a painstaking process requiring repeated observations and rigorous data analysis. Adding to the difficulty is the inherent rarity of stars like Caffau's. The vast majority of stars in the Milky Way have higher metallicity because they formed from gas clouds enriched by previous generations of supernovae. The extremely metal-poor stars are a tiny fraction of the total stellar population, meaning that wide surveys must examine millions of stars to identify even a handful of potential candidates. Once a candidate is identified, astronomers must confirm its properties with follow-up observations, often using multiple telescopes and instruments over months or years. This makes discovering a star like Caffau's a feat not only of technology, but also of patience and persistence. Furthermore, dim stars like Caffau's are particularly vulnerable to misclassification. Without precise photometric and spectroscopic data, they can easily be mistaken for more common stars, white dwarfs, or even distant extragalactic objects. Advanced techniques in calibration, data reduction, and error correction are critical to ensuring that what is observed truly corresponds to the star's intrinsic properties. Any error in measurement could misrepresent its metallicity, age, or even its very existence as an outlier among halo stars. Observational challenges are compounded by the limited number of suitable instruments. High-resolution spectrographs capable of resolving the subtle absorption lines in faint stars are typically mounted on the largest ground-based telescopes or on specialized space-based observatories. Access to these instruments is highly competitive, and observing time is limited, making each measurement of a rare star like Caffau's a precious and carefully planned endeavor. Astronomers must carefully schedule observations to avoid interference from the Moon, atmospheric conditions, and other stars in crowded fields, further illustrating the logistical complexity involved. Even with these instruments, faint stars demand long exposure times. Observing Caffau's star is not a matter of a few minutes or even a few hours. It may require nights of accumulated exposure, often with repeated visits to build signal strength while mitigating noise. During this time, atmospheric variations, thermal fluctuations in the telescope, and cosmic ray hits on detectors must be corrected meticulously, or the resulting data could be unreliable. Spectroscopic confirmation of extreme metal deficiency is particularly sensitive to these factors, since even a small artifact could produce spurious absorption lines that misrepresent the star's true chemical composition. The star's dimness and distance also affect the ability to measure other critical parameters, such as its mass, temperature, and age. These values are derived from models that incorporate spectral data, luminosity, and stellar evolution theory, and any uncertainty in the observational data propagates through to the derived properties. For Caffau's star, the margin of error in age estimation is significant, and determining its precise mass requires careful modeling to account for its faintness and low metallicity. Astronomers must rely on sophisticated computational methods to extract meaningful results from the scarce photons received from this distant, faint star. The observational challenges are not just technical, they also shape our understanding of the population of stars like Caffau's. Because these stars are so difficult to detect, our current census is almost certainly incomplete. There may be many more ultra-metal-poor stars lurking in the halo, or even in neighboring galaxies, remaining invisible because their light is faint and their spectral lines weak. Each discovery like Caffau's star requires immense effort, which means the apparent rarity of such stars may partly reflect observational limitations rather than true scarcity. Every additional detection expands our understanding of early star formation, chemical enrichment, and the extreme conditions that can produce stars with such anomalous properties. In summary, finding Caffau's star is a monumental observational achievement. Its dimness, extreme distance, low metallicity, and rarity combine to make it one of the hardest types of stars to detect and study. It is a testament to the precision, patience, and ingenuity of modern astronomy that such a faint, ancient relic has been identified and characterized at all. Every photon captured from Caffau's star carries with it information from the dawn of the universe, yet obtaining those photons requires overcoming enormous technical, logistical, and analytical obstacles. Its very discovery is as much a triumph of human persistence and technology as it is a challenge to our understanding of the cosmos. The discovery of Caffau's star carries profound implications for cosmology and our understanding of how the early universe evolved. At first glance, it is simply another star in the halo of the Milky Way, a faint point of light among millions of others. But when astronomers examine its chemical composition, mass, and age, it becomes clear that this star is anything but ordinary. It challenges foundational assumptions about star formation, chemical enrichment, and the conditions necessary for stars to survive for billions of years, prompting a re-evaluation of early cosmic history. One of the most immediate cosmological implications revolves around the process of early star formation. According to traditional models, the universe's first stars, population 3 stars, formed from gas composed almost entirely of hydrogen and helium. These stars were massive and short-lived, quickly burning through their fuel and enriching the surrounding medium with heavier elements through supernova explosions. Over time, this chemical enrichment enabled subsequent generations of stars, the so-called population 2 stars, to form from gas clouds containing metals, which facilitated cooling and condensation. In this model, low-mass stars with extremely low metallicity should be exceedingly rare, because small gas clouds lacking metals struggle to cool efficiently, making the formation of long-lived, low-mass stars unlikely. Caffau's star, however, is a low-mass star with almost no metals, yet it has survived for over 13 billion years. This contradicts the expectation that such stars should be rare or even impossible, forcing astronomers to reconsider the physics of early star formation. Its existence suggests that our models of cooling mechanisms in metal-poor gas clouds may be incomplete. Metals are critical in standard star formation theory because they provide radiative cooling, allowing gas clouds to shed energy and collapse under gravity to form stars. Without sufficient metals, clouds would remain hot and diffuse, preventing low-mass star formation. Yet Caffau's star exists, implying that there must have been alternative pathways for cooling and collapse in the early universe. Some theorists propose that molecular hydrogen, a less efficient coolant, may have played a more significant role than previously thought, or that local variations in gas density, turbulence, and magnetic fields could have facilitated the formation of low-mass stars under conditions previously assumed prohibitive. Each of these possibilities would require substantial adjustments to existing models of primordial star formation, emphasizing the star's role as a catalyst for revising cosmological theory. Beyond star formation mechanics, Caffau's star also raises questions about chemical enrichment timelines. The standard model posits a gradual, relatively uniform increase in metallicity over cosmic time. However, the star's extreme metal deficiency indicates that certain regions of the early universe could remain chemically pristine for much longer than expected. This implies that enrichment may have been patchy, highly localized, or delayed in some pockets of the cosmos. If true, it would require cosmologists to reconsider the homogeneity assumptions that underpin many models of early galactic evolution. The implications extend beyond individual stars. They could affect predictions for galaxy formation, supernova rates, and the distribution of chemical elements in the Milky Way halo. The star, in this sense, is not just an outlier, but a potential key to understanding the complex and uneven chemical evolution of the early universe. Another profound implication is related to the survival of early stars. Massive population 3 stars are theorized to have quickly ended their lives in supernova or direct collapse to black holes, leaving little trace of their existence. Low-mass stars like Caffau's star, however, can survive for billions of years, acting as fossil records of the early universe. Its existence suggests that, contrary to previous belief, pockets of star-forming gas may have occasionally produced low-mass stars, even under extremely metal-poor conditions. This expands the potential diversity of stellar populations in the early universe, and implies that the oldest stars we can observe today may represent only a subset of the types of stars that originally formed. Caffau's star, therefore, challenges astronomers to reconsider not only how stars formed, but also which stars survived and why. The star also has implications for the understanding of galaxy formation and structure. It resides in the halo of the Milky Way, a region thought to host remnants of the early galactic building blocks, small, ancient star clusters and dwarf galaxies that merged to form the larger Milky Way. Its presence in the halo suggests that some early star-forming environments could remain relatively isolated, avoiding the metal enrichment prevalent in more central regions of the galaxy. This finding may help refine models of halo formation and the assembly of the Milky Way, highlighting the importance of localized conditions and stochastic events in shaping the galaxy's oldest components. Cosmologists must now consider that ancient, nearly pristine stars could be scattered throughout the halo, each representing a distinct pocket of early universe history. Caffau's star also intersects with broader cosmological debates, including the timeline and uniformity of the Big Bang's aftermath. Its existence implies that the universe's early evolution may have been less uniform and more complex than previously thought. If stars like this could form long after the first supernovae, the standard narrative of a steadily rising metallicity gradient may require refinement. The star acts as a living record of conditions in the early universe that are otherwise inaccessible, offering a rare observational window into processes that shaped the cosmos in its infancy. Moreover, the implications extend to the search for other metal-poor and ancient stars. Caffau's star demonstrates that rare exceptions exist, suggesting that our current catalogues of ancient stars may be incomplete. If other similarly extreme stars exist, they could provide additional constraints on early star formation, chemical enrichment, and cosmological models. Each new discovery of this kind can either reinforce or challenge existing theories, making Caffau's star both a singular object and a harbinger of potentially many more surprises in the galactic halo and beyond. In essence, the discovery of Caffau's star forces astronomers to reconsider nearly every assumption about early cosmic evolution. From the physics of star formation in metal-poor gas to the distribution of chemical elements and the survival of ancient stars, it challenges conventional wisdom and opens new avenues for research. Its existence is a humbling reminder that the universe retains secrets even in its most distant and faint objects, and that our models, as powerful as they are, must remain flexible to accommodate the extraordinary. Caffau's star does not simply fit into the cosmic narrative, it reshapes it, compelling scientists to think in more nuanced, complex, and imaginative ways about how the first stars formed and endured. The discovery of Caffau's star naturally leads to one of the most tantalizing questions in modern astrophysics. Could there be more stars like it hiding in the Milky Way, silently enduring in the galaxy's remote regions, waiting for astronomers to uncover them? If a star this extraordinary exists, it is unlikely to be entirely unique, though its rarity is undeniable. The Milky Way halo, where Caffau's star resides, is vast and sparsely populated, stretching tens of thousands of light-years above and below the galactic disk. Within this immense and dimly lit expanse, countless stars remain undetected, particularly those that are faint, ancient, and metal-poor. The halo is thought to be a repository for the galaxy's oldest stellar populations, remnants of the first star-forming regions, and the debris of small dwarf galaxies cannibalized by the Milky Way over billions of years. Many of these stars have likely remained isolated, shielded from the chemical enrichment that transformed gas clouds in more central regions of the galaxy. This isolation increases the likelihood that other ultra-metal-poor stars, similar to Caffau's star, exist but remain hidden due to their faintness and remote locations. Detecting them requires wide-field surveys, high-resolution spectroscopy, and often years of follow-up observations to confirm their chemical composition and ages. Current surveys, like the Sloan Digital Sky Survey, SDSS, and the Gaia mission, have already revolutionized our understanding of the halo's stellar population. They have identified many low metallicity stars, some of which were previously unknown. However, these surveys cover only portions of the sky with the sensitivity needed to detect the faintest and most metal-poor stars. Given the sheer volume of the halo and the small fraction of stars that are exceptionally dim and ancient, the probability of undiscovered stars like Caffau's star is significant. Each new detection could reveal additional anomalies, further challenging our understanding of early star formation and galactic evolution. There is also the tantalizing possibility that stars with even more extreme properties than Caffau's star exist. Perhaps some formed from nearly pristine gas clouds that never encountered enrichment from population 3 supernovae at all. These stars would be extraordinarily rare and incredibly faint, potentially escaping detection by even the most advanced surveys to date. If found, they could provide unprecedented insight into the primordial conditions of the universe, offering direct evidence of environments previously thought inaccessible to observational astronomy. Discovering more stars like Caffau's would also allow astronomers to study patterns and distributions in the early Milky Way halo. By comparing the chemical compositions, ages, and orbits of multiple ultra-metal-poor stars, scientists could reconstruct the formation history of the galaxy in greater detail. It would help answer whether Caffau's star is an isolated anomaly, a rare survivor, or part of a small but distinct population of long-lived, extremely metal-poor stars. Each additional discovery would refine cosmological models, providing critical data points for simulations of the early universe, star formation, and chemical enrichment. In conclusion, the existence of Caffau's star opens the door to the possibility that many more extraordinary stars lie hidden within the Milky Way, silently preserving the secrets of the universe's infancy. Each undetected star represents an opportunity to expand our understanding of cosmic history, to test the limits of our theories, and to encounter anomalies that could reshape our knowledge of the cosmos. The halo is vast, ancient, and still largely unexplored, and within its depths, other improbable stars, like Caffau's star, may be waiting to reveal the mysteries of a universe far more complex than we have ever imagined. Caffau's star stands as a luminous enigma, a solitary beacon in the vast halo of the Milky Way that refuses to conform to our expectations. Its mere existence challenges the foundations of cosmology, reminding us that even the most robust theories are subject to the surprises of nature. For billions of years, this star has quietly endured, nearly as old as the universe itself, preserving within it a record of the cosmos's earliest epochs. Its extremely low metallicity, unexpected survival, and isolated location combine to make it not just a scientific curiosity, but a symbol of the universe's enduring capacity to astonish and confound. In contemplating Caffau's star, we are reminded of the limits of human knowledge. Theoretical models, no matter how sophisticated, are built upon the observations we have collected and the assumptions we make about the laws governing the universe. This star exists at the edges of those assumptions, a living exception that forces scientists to re-examine what is possible. It tells us that the early universe was more complex, more varied, and perhaps more unpredictable than we have imagined. Each photon of light reaching our telescopes carries with it a story that spans billions of years, offering a rare and direct glimpse into the conditions of the cosmos shortly after the Big Bang. Caffau's star also emphasizes the importance of exploration and perseverance in astronomy. The halo of the Milky Way, dim and difficult to observe, may conceal countless other relics of the early universe. Stars like this are not obvious. They require careful observation, precise instrumentation, and the persistence of generations of astronomers to uncover. Yet their discoveries have the power to reshape our understanding of cosmic history, revealing new insights into star formation, chemical evolution, and the very processes that created the universe as we see it today. Ultimately, Caffau's star inspires awe not just for its rarity, but for the profound questions it raises. It is a single star, yet it has the power to rewrite narratives that span billions of years and countless generations of stars. It serves as a reminder that the universe is far from fully understood, that mysteries linger even in the faintest points of light, and that our quest to comprehend the cosmos is ongoing. This lone, improbable star embodies the tension between human expectation and cosmic reality, a tension that drives science forward and sparks the imagination. In the end, Caffau's star is more than an astronomical object. It is a symbol of the universe's enduring capacity to surprise, a testament to the depth of the unknown, and a call to continue exploring the cosmos with humility and wonder. Its existence whispers to us across time, hinting that even after 13 billion years, the universe still holds secrets capable of reshaping everything we think we know about our cosmic origins. In the quiet brilliance of this star, we are reminded that the story of the universe is not yet complete, and that even a single star can illuminate mysteries far greater than itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.